Hello everyone, and welcome back to another study shed video. Today, we'll be going over the method of solving a first-order linear differential equation using the integrating factor. So last time we went over substitutions, and while it was fine and well, there are some equations that you can't really use a substitution method for. Like if you have a general equation like this, it's very hard to find a nice substitution like v equals y over x in order to apply. So in that case, we have something called the integrating factor. And to begin with, I'd like to derive how we get the equation to determine what this integrating factor is. So a general first order linear differential equation will look like something like this. And what we're going to do is we're going to try and derive an expression in order to apply the integrating factor. So what we're going to first do is we're going to divide all three sides of all three terms in this expression by f of x, giving us y prime plus g of x over f of x times y is equal to h of x over f of x. And for the sake of maintaining things nice and simple, we're going to make substitutions for these two. We're going to let this quantity be q of x and this quantity be p of x. So right now we have our differential equation, y prime plus p of xy equals q of x. So what will we do here? So we're going to focus on this right-hand side for now, left-hand side. And we'll notice that we have both a term, y prime and y. We have to notice the fact that y prime is the derivative of y. And seeing this, we should come up with something really quickly. And that is, this right-hand side, something had to have happened and a product rule should have taken place to get both y prime and y being added together. So our hint right now is that the product rule has been applied. And this is actually a really important hint. This is because it allows us to determine exactly what the integrating factor should be. So going off with our intuition that the product rule has been applied, we're going to rewrite this function as y prime plus pxy equals q of x. And we're going to take a look at this side again. So we're going to know that y times something prime equal to y times that function's derivative, we'll call that function f for now, is equal to, oh actually we already used f, we'll change the variable to something we haven't used, we'll call that o prime plus o times y prime, right? And so seeing this o here, we're going to multiply everything, this entire equation by o. And so what we're going to do, we're going to multiply this thing by o, and we're going to get o of x times y prime plus o of x p of x times y equals o of x times q of x. And the reason we did this is because we have a hunch that this function o of x is the other function that we took the derivative of in order to get this product rule expansion to work. So we have this term here, o of x times y. That exactly matches our second term in our product rule expansion. So that means this second term over here, o of x times p of x times y, is somehow related to the function y times o prime. And this gives us a huge clue. So with the clue we had, what we're going to do is we're going to set up our product rule on this side. We're going to have y prime times o of x. I'm going to write small little. Y prime times o of x plus o prime of x times y is equal to y prime of x times o of x plus o of x times p of x times y. We're going to get rid of these two terms as they're common. We're going to get rid of the y's because they're also common. And we're left with the expression o of x is equal to o prime of x is equal to o of x over x times p of x. And this is our final clue. What we're going to do here is we're going to solve for o of x. So now we're going to solve for o of x. So what we're going to first do here is we're going to bring this o of x over here. but we're going to divide both sides by O of x. We can get O prime of x over O of x is equal to P of x. Right? And so what we're now going to do is that since we know O prime of x over O of x is equal to P of x, we're going to integrate both sides. We're going to integrate both sides with respect to dx. I'm going to shove in a dx there. Let's make the integral sign nice. Integral sign right there. And here's our integral expression. This side evaluates to ln of O of x, as by chain rule, we know that the derivative of ln of O of x is equal to 1 over the function times the derivative of the function. And this side we're going to keep as P of x dx. Right? And we're going to raise both sides. We're going to raise both sides with base e to get e to the ln O of x is equal to e to the integral P of x dx. And we can rewrite this side completely. You can rewrite this side completely. It's just O of x. And this is our integrating factor derived. So the function that we multiplied all two sides of the equation by, O of x, is actually has a general expression. And this equation is very important to memorize. Notice I'm highlighting all the colors because you have to know it. So again, what is P of x? If you have a differential equation, which I will rewrite, if you have a differential equation, dy over dx plus P of x y equals q of x, e to the integral of this function right here, P of x dx, is going to be our integrating factor. And the reason we'll use this integrating factor is if we multiply, that's not a parentheses. Right? The reason we'll use this integrating factor is if we multiply the entire equation by O of x, we will be able to apply product rule on this side. And so let's work out an example. Alright, so our question, which we should do, is cosine of x times dy over dx plus sine of x y is equal to, let's just do 1 for now. So how would we do this? How would we start? So our first step is going to be, you're going to get this dy dx on its own. Right, so we're going to divide everything by cosine of x to get dy over dx. Plus sine x divided by cosine x is just tangent x, so I'm going to write that here. Tangent of x times y. And then 1 over cosine x is just secant x. Right? So this is our differential equation now. So now we'll identify this as P of x because it is the function that is multiplying y. And we're going to integrate P of x. So actually I'll just straight up write tangent of x dx. That is a very elementary integral. It's ln of secant x. Obviously, remember, plus c. Right? So ln of secant x plus c. So we have e to the integral, or we already integrated it, so we have e to the ln secant x plus c. So this is our integrating factor. We're going to simplify this. We're going to just write O of x first. We're going to simplify this to get b e to the ln secant x. So our integrating factor is just b e, not even e, absolute value secant x. And we can break the absolute value to just get some constant c. Oh, we already used c. Some constant a times secant x. So this is our integrating factor, O of x. Integrating factor. This is what we multiply our equation by in order to solve it. So let's go back and plug this in. So our differential equation was dy over dx plus tangent of x y is equal to secant of x. We're going to multiply every side of the equation by secant of x. So you get secant of x dy dx plus secant x tangent x tangent x y is equal to secant squared x. And notice over here we have our perfect product rule expansion. We have secant x and y being our terms, as the derivative of secant x is secant x times tangent x, and the derivative of y is just dy over dx. So we're going to rewrite it like this: secant x times y prime is equal to secant squared x. And we're just going to integrate both sides with respect to x. The integral of the left side is just secant x y plus some constant c1. And the integral of the right hand side is our favorite tangent x integral plus another constant. And we're going to combine the constants. We're going to combine the constants to get secant x times y is equal to tangent x plus c. And now solving for y, we're going to get y is equal to tangent x times cosine x plus c times cosine x. Remember that. The c also gets multiplied. And so we simplify this to get y is to get sine x plus c times cosine x. Let's fix the c. Right? And if we had a initial condition, we will plug in and be able to solve for c. But this is our final answer, and this is how you solve it in a differential equation using the integrating factor. So recap. How would we solve an equation using the integrating factor? First step we're going to do is we're going to isolate dyd over dx, but not keep it on its own side of the equation. Our second step is to identify p of x, integrate it, and then remember we have to put that it's e to the integral of p of x, so we're going to have to simplify that expression. P of x, let's fix this e. Right? We're going to simplify this expression, and this is our integrating factor of x. You can use any letter. Remember right there we're going to multiply, and then use product rule. Reverse the product rule essentially. Product rule. That's the whole point of using the integrating factor. We just integrate both sides after that, and we solve and isolate for y. And that is using the integrating factor. Thank you for watching this video. Hopefully you learned something today. And as always, happy studying.